The semiconductor industry has been built for decades on one unspoken rule. Without the right equipment, there are no advanced chips, no exceptions, no workarounds. But that rule is now cracking at the seams. The company that was cut off from the most critically important technologies in the world has announced an approach that potentially allows it to bypass the very concept of an advanced manufacturing process, without the machines that were considered absolutely indispensable. If the claimed numbers turn out to be real, this isn't just an engineering achievement. This is a rewriting of the rules of a game where the winners seemed predetermined from the start. For roughly 6 decades, the entire technology industry has moved along a single trajectory. Transistors shrink, chips get faster. Chips get faster, computers get more powerful. Computers get more powerful, the world changes. This idea became known as Moore's Law, and it worked so consistently that the industry treated it almost like a law of nature. Roughly every 2 years, engineers found a way to shrink transistors again, double their count on a die, and performance would take another leap. We went from thousands of transistors on a chip in the 70s to billions in the 2000s to hundreds of billions today. The smartphone in your pocket has more computing power than supercomputers that filled entire buildings just a few decades ago. But there's something that marketing presentations prefer to stay quiet about. That progress is slowing down. Leaps that used to happen every 2 years now stretch to 3 or 4. Building a single modern chip fabrication plant costs around $20 billion. Developing one new generation of transistors can cost $1 billion before a single chip is ever produced. The leading Taiwanese manufacturer is fighting for an area gain of around 6% in the next generation. 6. It used to be 50% or more. The easy wins are gone, and the hard ones keep getting harder. For one specific company, the problem is even more acute. It's not just about slowing progress, it's about a decision made in Washington. In 2019 and 2020, the American government imposed sweeping restrictions on technology exports to Huawei. By 2022, the company was effectively cut off from the most advanced chip manufacturing equipment in the world. The key piece of that equipment is the extreme ultraviolet lithography machine. It's made by the Dutch company ASML, and nothing comparable simply exists anywhere else in the world. This machine uses a laser to vaporize tiny droplets of tin, releasing enough energy to create plasma that generates extreme ultraviolet light. That light is then reflected through a series of mirrors so precise that even a single atom of contamination can ruin them. Using this light, circuits are printed onto silicon so small they can't be seen under a regular microscope. Each of these machines costs around $200 million, weighs roughly as much as 2 passenger aircraft, and it's what allows the world's leading manufacturers to produce chips at 3 nanometer and 2 nanometer process nodes. Huawei cannot buy one. Chinese chipmaker SMIC, which produces chips for Huawei, cannot either. So what do you do when the industry's primary tool is out of reach? You find another way. SMIC has done impressive work with older equipment. The company uses deep ultraviolet lithography machines with a less powerful type of light. DUV was never designed to produce chips as miniaturized as what SMIC is achieving today. To get around this limitation, a technique called multiple patterning is used. Instead of printing a complex pattern in a single step, it's broken down into several simpler ones, each performed separately, then everything is aligned together. Think of it like painting a detailed picture by laying down one color at a time. Through sheer engineering persistence, SMIC has managed to reach a level roughly equivalent to a 7 nanometer process node. That's genuinely impressive, but every additional step increases cost, complexity, and the probability of error. And this approach has a ceiling. Huawei understood that. So the company's engineers started asking a different question. What if transistor size isn't the only way to make a chip better? Here's a surprising fact that changes the whole picture. Modern computers are increasingly less constrained by how fast transistors switch. The main bottleneck today is the time it takes to move information around inside the chip. The computation itself is no longer the bottleneck. The data transfer is.
According to Huawei, in modern computing systems, more than 80% of energy is spent on moving data rather than on actual computation. The chip spends most of its time acting as a courier, not a mathematician. To understand why, think of a chip as a city, a tiny city with hundreds of billions of tiny workers packed into an area smaller than a fingernail. Those are the transistors. They perform calculations, but they're connected by a network of metal rods, conductors that run through more than 20 layers inside the die. Every time a signal travels along one of those conductors, two things happen that slow it down. First, the wire resists the passage of the electrical signal, kind of like a narrow pipe slowing down the flow of water. Second, the wire behaves like a tiny capacitor that has to charge and discharge every time a signal passes through. Engineers call this RC delay. The longer the wire, the stronger both effects become. That's exactly why processor clock speeds have barely changed over the past 15 years. We're not limited by the speed of transistors, we're limited by the speed of signals traveling between them. And here's the key insight.
If the problem is distance, what if you could simply reduce the distances? Not by shrinking transistors, but by rearranging them relative to each other. What if, instead of laying a chip out flat, like a city on a plane, you stacked its parts on top of each other, like a skyscraper? That's exactly the essence of what Huawei has announced. The company calls the approach Tau scaling, and the concept is fairly intuitive. Take a sheet of paper covered in text. The words in the top left corner are far from the words in the bottom right. Now fold the sheet in half. Words that were separated by inches are now right next to each other, separated only by the thickness of the paper. Huawei wants to do the same thing with a chip. Take a processor that normally lies flat, split the logic, and fold one half on top of the other. Signals that used to travel several millimeters across flat silicon now travel a tiny fraction of that distance vertically. Millimeters become microns. Latency, power consumption, and heat generated by moving data drop sharply.
In early results, Huawei reports a transistor density of 238 million per square millimeter using this stacked approach, roughly 55% more logic in the same area compared to a flat layout. And in a roadmap extending to around 2031, the company claims performance equivalent to what's expected from a 1.4 nanometer process chip. All of this without EUV lithography. It's worth pausing here because a lot of press headlines have misread this claim. When chipmakers talk about nanometers today, those numbers are more of a marketing label than a physical measurement. Huawei is not claiming it has created a new type of transistor that is 1.4 nanometers in size. The company is saying that by stacking two layers of existing chips on top of each other, it can fit enough transistors into a given area to compete with what is described as a 1.4 nanometer chip. That's still impressive, but it's a different kind of achievement. A systems-level technique, not a transistor-level breakthrough. The real breakthrough, if it's actually realized, lies elsewhere. In a number that caught the attention of every semiconductor engineer. Not 1.4 nanometers. A different number, 1.5 microns. That's the target bonding pitch for the connections between layers in the stack. When two chips are stacked on top of each other, they need to constantly exchange data, billions of times per second. That communication happens through tiny copper pads that directly connect the layers. The smaller those pads and the more densely they're packed, the more connections fit and the faster information can be transferred. The distance between those pads is called the bonding pitch. Today, the best figure in the world is around 9 microns. That's the pitch AMD uses in its three-dimensional memory chips. TSMC and Intel are in roughly the same range.
Huawei is targeting 1.5 microns, 6 times smaller than the current world record. Going from 9 microns to 1.5 is not a small step. It requires new equipment, new materials, new processes, and new methods for verifying connection quality. That kind of leap typically takes the industry a decade, advancing gradually. If Huawei pulls it off, with enough connections between layers, two stacked chips will stop behaving like two separate devices and start functioning as a single dense processor. The boundary between them will disappear from a performance standpoint. But this is where physics enters the story. Memory chips run relatively cool, they just store data. Logic chips are a completely different story. They switch billions of times per second, and every switch generates heat. Multiplied across hundreds of billions of transistors, that's a lot of heat. Right now, it escapes through the top and bottom surfaces of the chip into a cooling system. In data centers, that system can be enormous, but Huawei's first target for this technology is not a server chip, it's the Kirin mobile processor. In a smartphone, there are no fans, no liquid cooling, no room for anything like that. There is a thin metal plate and maybe a small graphite sheet. And the device sits in your hands so it can't get too hot, otherwise it becomes uncomfortable to hold. When you place one hot logic chip on top of another, the heat from the bottom layer has nowhere to go. The top layer traps it. You end up with a tiny thermal sandwich and the filling burns. This is not a minor engineering challenge. It's one of the most difficult physical problems in the industry right now.
Some research groups are looking into materials with better thermal conductivity, or microchannels inside the silicon itself to pump coolant through. But none of these solutions have been proven at mass production scale yet. The answer to the thermal problem is exactly what determines whether tau scaling is a real roadmap or just an impressive presentation. The announcement is real. The engineering challenges are real. The outcome is unknown. Now for the bigger picture. Even if everything works, what does it actually change? Moore's law was unique in that it simultaneously made chips better and cheaper. Each generation delivered more performance at a lower cost per transistor. Tau scaling doesn't work that way. Stacking chips costs more than laying them flat. A bonding process at 1.5 microns will cost more than at 9 microns. You're trading cost for performance. You get more capability in the same area, but you pay more for it. In a world where traditional scaling has slowed down, any path to performance growth is valuable. But this is a different kind of progress. It's worth noting, Huawei is not alone in this direction. AMD already stacks memory on top of logic. High bandwidth memory stacks multiple dies on top of each other. Intel and TSMC have their own three-dimensional packaging programs. The industry was already moving this way. Huawei is simply pushing that movement harder and faster, partly out of necessity, partly because it has the engineering talent to make the attempt. The company's roadmap runs to around 2031. A lot can change in that time. The near-term key questions. Can SMIC manufacture stacked chips at scale with good yield, meaning a high enough share of working chips out of total production? A chip that performs brilliantly in the lab but only comes out functional a fraction of the time in manufacturing is not a product. And the thermal story. As details emerge about how Huawei plans to handle the heat problem in a stacked mobile chip, it will become clear how much of this is real production thinking versus just ambitious slides. If the 1.5 micron bonding pitch is achieved, other companies will want the same. TSMC and Intel will accelerate their own programs. The race won't end. It'll just move to a new arena. And that's both the beautiful and the agonizing thing about semiconductor engineering. Every time someone says, "That's impossible," someone else goes and does some version of it. Not always the way the skeptics expected, and not always on the promised timeline, but eventually.
Huawei's announcement is not proof of victory. It's proof that the company is in the game. And in a game of this scale, that already means something. If you enjoy actually understanding how technology works, hit the like button. It genuinely helps the channel reach more people who care about topics like this. Subscribe and hit the bell so you don't miss the next video. And drop a comment below. Do you think Huawei can solve the thermal problem and make this work in a real smartphone?